video, we'll discuss section 15.2, something called line integrals. Okay, so we're going to go back to Calc 1, and maybe you've seen this, maybe not, and maybe you haven't. And if you haven't, that's okay. I know, like in Calc 1, for me, I typically will push past this pretty quick or skip it altogether. So from Calc 1, we have this integral, and this represents the mass of a straight wire. So it'd be like if we had a straight wire on our graph from A to B, and we were just running from straight to there, right? If the function f of x is the mass density function, then we are finding the mass of that wire. So if f of x represents the density at any point of that wire, the integral from A to B will find the density of that straight wire. Now, the problem that we're leading to now is, since dealing with in 3 space, and we have vectored value functions that follow this line in space, we could have an A and a B, but since it's in space now, the wire could do something like this, right? Does this mean we could still find mass? Yes, but we're going to have to change it just a bit. We're going to change it to 3 dimensions. I'm going to talk through it really quickly, pretty quickly, on the method that is taken, and then I'll show you quickly through the theory. The problems themselves, I think, are easier than the theory in this case. So when we're dealing with a wire that curls on itself like that, because I couldn't do A to B, what I'd be dealing with now is we could actually describe this in 2 variables, an x and a y, with a vector. And what we could do is think about that this function, we have x and y, right, x and a y, and this function will come out at us in 3 dimensions. So what we're actually going to do is think about this as like a rolled up piece of paper standing on its side. So you have it looking down on a piece of paper that's rolled up, sticking up at you. And we are going to find the mass of this by thinking about that paper, right? So what I mean by paper is like it would look like this, like on its side, and then it would like roll on itself in here, right? So like standing it up, what we could actually find is the height, so how tall it is, and then we could take a small little segment here and do a bunch of very small segments with that height, and then run all these little segments together. So it's an area problem. It's how far did we go times how far did the function go up from the xy plane. And then we add those all together. Well, that function itself would be a mass density function if we're looking for mass. So that function, though, now is in terms of x and y. I don't need just an x. I need to know an x and y. And then this ds, remember, this is arc length, right? This is adding the arc lengths up to get the mass of that wire. So this tells the mass density, right? How much do we have in each one? And then this is the length of the wire almost. But we're thinking about it differently because we are thinking about it in 3 dimensions, so it's a height rather than a distance to the side. If that is mass density, this still gives me the mass of the wire. I just have to deal with this weird integral here. So we have this integral over some curve C. This would be our C, this function. That's the path, while this is the function in space. C is the path we're walking on. The function inside the integrand is the function we are dealing with. Or it's giving the density of a wire, if that's what we're talking about. We're going to work on this integral. We're going to define C using parametric equations for ds using arc length. What that means, okay, so let's work through this. F of xy is a surface, gives a height above each point, C. So we have some like curve C, right? We just looked at some curve that looks like this. Some curve C, and we would have some kind of function r of t, and this would be some kind of x of t, I, plus y of t, j. That would describe this wire. I would need the x and y because it's going on itself. Thus, when we do this, we just talked about this, finding the areas, and it gives the area under that function, but only over C. So that's what we're doing is, this is a function coming out at us in the Z direction, but we're finding all the little areas. Remember, this is like a piece of paper going straight down. We can't see it like that, but it would be holding your paper up and curling it. I have a height of the paper and then the width. So if I do it over all of C, that's what this is. Now our goal is to go from two variables, because right now we have an x and a y, right? The x and the y would describe this function. I would really like to get it down to one variable. Well, vectors would be our answer. I would wonder, this is putting, remember, this is a fancy way of saying putting f of x, y in terms of t. So that'd be like replacing your x and your y with things that define it in t. Now, ds, this is arc length. And I don't know if you remember, but this is from, I think, Calc 1 or 2. We actually also use this definition sometime in this class. R of t is the curve that we're moving along, defined by x and y. Well, I can actually take that, and remember, this is what ds is representing, right? ds is that dt. But notice, if I define a function, xt and yt, and I take its derivative, and then I take its magnitude, what's right here? This whole thing? And those t's are typos, so forgive me. But that is the same thing as that. So that's supposed to just be a normal t in here, along with the y one as well. But it's the exact same thing, so I can rewrite ds, that's arc length, I can rewrite it, the magnitude of my curve, dt. And that just comes from this idea in Calc 1, 2, and some of what we did this semester when we talked about the length of a curve. It comes from that, right? So what that means is now this becomes some function now turned in t's, right? X's and y's are t's now, times the magnitude of that function that defines them. So that actually would give us the length of that wire. So we could also think about it as area, right? It's the area under the curve along C. This is going to help us going into where we're going. As of right now, it just finds the length of the mass of a wire if the f function is the mass density. It also will allow us to do integrals that are set up like this. So let's give this a shot. So here's my integral. We're doing the integral of y, and it's a line integral because this is a line. It's not a straight line, some kind of curve, some kind of line that's defined, right? We could follow the t's, and then they tell us it's from 0 to 1. We can actually use this to answer this integral. We can use the same logic that we just thought of. Okay, so f of xy, in this case, is whatever is in the integrand. So that's y. I can also change this. This fancy notation just means take this notation and put it in form of t. Well, I don't have an x and y yet, but I can grab them from here. X of t equals 2t. Y of t equals t cubed. Right? I grabbed it. That's my x and my y. So I can just replace, okay, y is t, so the f function, capital F, right, is, or lowercase f, I guess, in this case. We're going to use an uppercase f here later in this section. So f of that and f of that. All right, and then I also need, okay, so I have r, but I need r prime. That's going to be 2i plus 3t squared, j. And then I'm going to need its magnitude. All right, doing that, that's the square root of, all right, plugging all that in, I got 4, plus I squared the next one, 9t to the 4th. Great. All right, so that means that this integral c over c, that curve, y ds, is the same thing as t, we're going to switch them to t, and they told us the t, 0 to 1, right? And then we just take the function that's now, remember it was f, let's just write this out, f of x of t, y of t, that's f in terms of t, times the magnitude of our curve that we're going along, dt. All right, so I just replace everything. T equals 0 to t equals 1. That thing was t cubed times, okay, we get the square root of 4 plus 9t to the 4th dt. Now this is just a function in terms of t. I'm not going to actually do the integration through any of these steps. I'm going to set it up and then trust that you can do that integral problem. This would just be a u sub. If you want to work it out, the answer is 1 over 54 times 13 squared of 13 minus 8. Work that integral out and match that if you would like to practice your integration. I want to keep the video short by just setting it up and then giving you an answer. All right, let's take a look at the next integral. So remember, that is given, we don't want to lose sight of what we're doing, given that y is the density function of this wire we're talking about, we found the mass of this curved wire that follows that C, that path C, from 0 to 1. We just found the length, the density of the wire, if y was the mass density function. We're just really learning how to evaluate these integrals. All right. So we have this integral. All right, same setup. Okay, we're going to want to start drawing pictures. We're going to have pictures of our XY plane. Our XY plane, okay, so that's a circle. And this is the right half of the circle of radius 3. All right, so we have that curve. And it says the right half of that. And then they give us, let x equal r of that. So we can actually write these down. I have a radius, so I don't need to put r. The radius is 3. So I got 3 cosine theta. I got y equals 3 sine theta. And even though they didn't give us a function, we can actually make one now. R of t is equal to 3 cosine theta. I'm going to use bracket notation. And 3 sine theta. And then let's not call these thetas. Let's call them t's. Just because that's what we're used to. Okay, so I have r. Now I just find r prime. So we get negative 3 sine t, comma 3 cosine t. And then we have to find the magnitude of that function. All right, so we got the square root of 9 times, I'm going to go ahead and factor the 9 out because I'm going to have it in both, sine squared t plus cosine squared t. That's a 1 inside the parentheses, so this is the square root of 9, which is 3. All right, I also need my function. F of xy was equal to x squared plus y squared. All right, I'm going to replace x of t, y of t. This just means putting it in terms of t. Right, I have x and y, so I'm going to have 9 cosine squared t plus 9 sine squared t. All right, so now we can set up our integral. We have the integral from, okay, we do have to figure out what t should be. Okay, to get cosine down here, that's all the way down to negative pi over 2. So it's going to be t equals negative pi over 2. And then to get it all the way around, or to the top, I mean, we have t of pi over 2, right? Down below to up above. Right, then we do 9 cosine squared t plus 9 sine squared t. And we times that by the 3 dt. 3 was the magnitude. All right, so this actually works out. If you want to try to work it out, this one's okay because that cosine sine squared was going to make things fine for us. This becomes 27 pi. I'd encourage you to work it out. But that is the mass of the wire if the function in the integrand, x squared plus y squared, is a density function for whatever we're talking about. All right, I got a few more examples. Now they're going to give us a segment. You're going to say, we're going to go from this point to that point. Here's a formula for that, but the way I like to think about it is y equals mx plus b, or in this case, to help me out, I do y equals b plus mx, or mt rather. So each function, my x of t, it starts at negative 2. That's what b represented. Remember the y-intercept, or the starting point. And then I check out how much does it grow. Okay, negative 2 up to 1, that goes up 3. So that is my slope, t. That's how I do it. X of t is that. Y of t, okay, the point starts at negative 1. And from negative 1 up to 3, that went up 4. That's how I go about that. That gives me r. All right, that's negative 2 plus 3t I plus negative 1 plus 4t j. All right, we need the derivative of that thing. So we get 3i plus 4j. All right, I like those numbers because this is going to be much easier. The magnitude of a 3 and a 4, right, that's square root of 9 plus 16, which is 25, which gets me a 5. This is great. We can set up our integral now. So the integral over c of 2xy ds is equal to the integral from t equals 0 to t equals 1. And I'm going to replace each one. 2 times negative 2 plus 3t, that was x. Then y, negative 1 plus 4t. That came from here. What I'm doing is replacing x and y. And then I can replace with 5 dt. That takes care of the ds. This, I'm not going to work out, but if you'd like to work it out, the answer turns out to be a nice, pretty 5. So work that out. Make sure you can do it. More than likely for your final or your test, whatever's coming next for you, depending on which class you're in, which semester you're in, I will have you set it up and stop. I'm going to have you do a lot of that because I don't really care at this point. I hope you can integrate. I mean, I do care, but we're not working on integrating. You need to have that down at this point. All right, I got another example. Now we have 3 points. It's also segments, so a straight line. How we set this up, there's a formulas there if you'd like to set it up. I like using mx plus b. So my x of t starts at 1, and then I just think about, okay, 1 to 2, it went up 1, so that's 1t. Y of t starts at 1, and it goes up to 3, so that went up 2t. And then z of t, that started at 0, and it went up from 0 to 1, that's 1t. So I could put 0 plus 1t, I'm just going to put a t. That describes my path. All right, so the path here is 1 plus 1t, comma, 1 plus 2t, comma, t. We can find the derivative of those. We get 1, 2, 1. All right, and then this calls for us to find the magnitude. So that's the square root of 1 plus 4 plus 1, which is the square root of 6. All right, we have everything now. We could just plug it in. So the over c for this segment, x, y, z squared ds is equal to t equals 0 to 1. We always want, if we create these, that's how it's always going to work out. You should check those, by the way. You should plug in 0 and plug in 1 and make sure you get 1 point and then the other. Now I'm just going to plug everything in. 1 plus 1t times 1 plus 2t times t squared. Or don't forget, square root of 6 dt. This is going to work out, once you do all the calculus, to be the square root of 89 over 60, square root of 6. Oops, sorry, I dropped my pencil. All right, I have one other problem, or a couple other problems here, and then we're going to change gears a bit here in 2 problems. Sometimes they won't do just an integral with respect to s. What they'll do is an integral with respect to dx plus dy dz, and it's the same. It's the same-ish. We can't just change it back to the other thing because how would we do that? But it's still a line integral. So we have 2 segments here. We could draw pictures from 1 to 2 to 3 to 4, and then 3 to 4 to 4 to 0. So we're going to actually write 2 different problems. The first one I'm going to do is I'll call x1 of t. And we set this up the same way. It started at 1. It went from 1 up to 3. That's 2. So 2t. y1 of t is equal to 2 plus 2t. All right, I'm going to move this over because we're going to do something with it here in a moment. I'll show you how to deal with some of the stuff on here. I also have x2t. That's the other segment. That's going to be 3 plus t. And then y2 is from 4 to 0. So it starts at 4 and then it goes down 4. So minus 4t. All right, this is what makes these problems a little quicker when they're set up like this. I have an x. To get a dx, and will be dx1, I just take the derivative. I get 2 dt. Here, I get dx2, 1 dt. dy1 is equal to 2 dt. And then the last one here, dy2 is equal to negative 4 dt. I have all the conversions that I need. Now, I do have to figure out my t's. So how we're going to split this up is we're going to take that integral and we're going to split it between two. So I'll write that first. xy dx plus xy dy is going to be the same thing over c1. And we got to write it out twice, unfortunately. Plus the integral over c2. And we're going to treat these as two different problems and then just add our answers. All right, our t's, anytime I set it up the way I set it up, it's t equals 0. So let's do each one. The first one is t equals 0 to t equals 1. It's always that if you set it up with a segment. And then I just replace, okay, so 1 plus 2t times y, 1, which is 2 plus 2t, times dx was 2 dt, plus, now I do the second half as x plus y, so 1 plus 2t plus 2 plus 2t times dy, which was 2 dt, plus t equals 0 to t equals 1 of the other one. So now I have 3 plus t times 4 minus 4t times dt, that's dx, plus those added together, 3 plus t plus 4 minus 4t, all times dy, and that was negative 4 dt. All right, what you do is just combine like terms. Your dt's can be like factored out and put together. So like you could, if you wanted to, put all your t's together there, multiply them out, add them, put it together. Then you'd have one integral with dt, then you'd have the second integral with de. All that works out to 22 over 3. If you need help working out, just multiply and add everything together. You could even, if you wanted to, put an integral in here, right? Since we have dt's, you could do that. I trust that you can do that because this is just Calc 2 at this point. Just work it out to get 22 over 3. Once you get it to this point, if you wanted to plug it all in your calculator, 0 to 1, and then just put everything that's in the integrand with dt, you could do that and let it do it all for you, meaning you're going to put this plus this with one integrand, 0 to 1, dt, and just distribute and add everything together. But only one dt and one integrand. Okay, I got one more example like this that's just going to look slightly different. Okay, so I didn't put t's when I typed this up, and I discovered that when I was looking over my notes. The t's here go from 0 to 1. Surprise. Okay, so we don't have x and t's defined for us, but I have a function that would define nice x and t's, x and y's and z's. X of t is e to the t. Y of t is e to the negative t. And then z of t is equal to 2e to the 2t. All right, we can use this to get dx's and dy's. dx then is e to the t, dt. This one is dy. dy is going to be negative e to the negative t if we take the derivative. And then this last one, this is dt. dz is 4e to the 2t. I can actually define my function now. R of t is equal to, and I'm going to put these in brackets. We don't even actually have to do that in this case. We just plug it in. So that is, I'm not going to rewrite it, but we get the integral from t equals 0 to 1, and then we plug all this in. Okay, so we got e to the t plus e to the negative t, dx, which was e to the t dt, plus e to the t times e to the negative t times dy, which was that whole expression, and then plus y, which was e to the negative t times dz, which is 4e to the 2t. Okay, all these have dt's at the end. I should do that one. So I can rewrite this, and I'm going to combine like terms. Check yours with mine. I get 0 to 1, and then I'm going to have e to the 2t plus 1 minus e to the negative t plus 4 e to the t dt. You can work this out. taking your, actually I may mess that up, one sec. Nope, we're good. Okay, this integral ends up being, it's kind of weird, but it's just because we can't add things together at this point. I got e to the second, e to the first. I got a 1 over e minus 9 over 2. I'd encourage you to work that last integral out, but it's just a Calc 1 review. All right, that's how we do those integrals. This is called a line integral. It is the integral over that path, giving some kind of mass density function. Now, we're going to change gears just a bit. Let's talk about, and we haven't really brought up any of the vector field stuff from the first section. This is where it comes into play, and it actually comes into play for the rest of the semester. So we are given a vector field. Now, remember, a vector field is like a force field, right? It has a bunch of arrows. So we're given a vector field. So here's some type of vector field, and then we're given some path. What we're doing is we're going to talk about a particle moving along that path, this path, in space, x, y, and z, it gives me where it's going to be, through this vector field. Think about a vector field. Remember, the vector fields were the like coordinate planes with all the arrows pushing you in different directions. So the idea, if I'm walking on a path or a particle's moving through a path in space in a vector field, like this path is inside, it's like a bunch of wind, a force field. You can think meteorology with this. Things are pushing you around in this vector field. Now, if we're working this out, a vector field, remember, this just means take F and put it in terms of T. And then this is our R prime. Now, I want you to think this thing, if we think about the rate that something is moving, right? With time, it's going to work out to be, we just use shorthand dr. That is the derivative of our r, of our vector, over time. Now, this doesn't look like it's very close, but this integral means work. So when we take a integral of a vector field over some path, we actually find the work, and this maybe is related to, right, F, what is it, F dot of displacement, D for work, dr, r being displacement, distance, and r, so that comes from that. So this is work. So it's like taking a vector field. So think about, you're in a room, a controlled room that has wind somehow, and all these winds are pushing you around, and we put a little roller coaster in the room, and we talk about how much work does it take for that cart to go around the roller coaster with all those winds pushing it around. It's pretty cool stuff. We're going to work our way, starting basic with two-dimensional curves on XY plane, and then work our way up into right before we start making the path three-dimensional, meaning it just doesn't stay on the XY plane, and then we're out of time. So I'll have one more section that I'll post a video of somebody else teaching it that will describe how this all ties together in the end. Okay, so let's get a few of these problems under our belt. So it says find work by moving along the parabola. So we're in two space on the bottom, and we have this parabola that looks like this, and they want us to travel on this parabola from -1, 1 to 2, 4. So it's like we're moving, from here to there, right? It goes from this point to that point in this vector field. So whatever that may look, and just like that section, we could graph that, go to every x and y and plug in an x and y, and then make our arrow point the direction that the force field is pushing. But we're not going to do that. So this is moving in the xy plane, or you could think about in 3 space, it's the ground, z going up. So we have some vector field. We're going to talk about how much work to get through there. So the first thing we're going to do is we have to define r of t, which we don't have here, but this is called the trivial way to do this, and this is what this is supposed to be for. For non-segments, not a straight line, do trivial parametric equation setup. So what that means is I'm just going to let x be t. If x is t, well, here's an equation that relates the two. Y is t squared. There's my function. It also works here from t. All right, this is the weird thing. Usually we wanted 0 to 1 to make our lives easy, but if I plug a 0 into this, I don't get -1. It would have to be -1 up to this 2, and we need our y's to make sense too. If I plug in -1 here, I do get a 1. If I plug in a 2 there, I also get a 4. So those are my t's. So according to everything we just done, we need the derivative of this. Oh, I do need to mention something up here. You should add this into your notes. This is a dot product, right? That's why, and maybe you're wondering, why did we not have magnitude just like in the previous problems? Well, if I take r prime as a vector, if I take the magnitude, it's no longer a vector, which means I can't do my dot product. So in this case, we want to find r prime, but we're going to leave it as a vector. So we have that. We also want to have f of xy. We want to change that in terms of t. So that's x of t, y of t. That's what this thing means. So we're going to change it. So f is this function right here. And I know x is t. We could even write this. We want x of t equals t. And y of t equals t squared. We're going to plug that in. So t times e to the t squared, I, plus, okay, y is t squared j. All right, I'm going to write these out in bracket notation because it helps me. Let's do r prime dotted with f. So this is the 1, 2, or 1, 2t dotted with t e t squared, comma t squared. Remember, dotting, I just multiply and add. So 1 times the first component, so there's t e, let me redo that e, t e to the t squared plus 2t times t squared is 2t to the third. That is my dot product. So now I can find the work done. The work done is from t equals -1, that was the ones we came up earlier, -1 to 2, of that dot product, t e t squared plus 2t cubed dt. Right, I'm not going to do the integral. The integral comes out to this. It's pretty crazy looking, but you can try to match it. There we go. All right, so the hardest part's going to be the setup, but as long as it's a line integral, all you got to do is find that curve like r, find the derivative. If it's a work problem, you don't take the magnitude. You just leave it as a vector because you're going to dot it with the vector field. So what we found is this is the amount of work it would take to walk along that path of the parabola up there, given it's in this vector field. It's pretty powerful stuff here. All right, I got one more problem. So again, find work. They gave us a vector field, and then they gave us a path. This path we can define. We've done that. If they don't tell you it's a specific curve, then it's a straight line. So -1, it went up 2. I'm going to move this over. Y of t starts at 3, and it's going down to -2, so that went down 5. Z of t, you can subtract these two if you'd want. Starts at 2, and then do 4 minus 2 is 2. So 2t. All right, so now we have a path. R of t is -1 plus 2t, I, plus 3 minus 5t, j, plus 2 plus 2t, k. All right, we can find r prime now. And then I'm going to dot, so I'm just going to go ahead and go to my brackets. And you'll see why too. This cleans up real nicely. The derivative of that I term, it's a 2. Derivative of that j term is a -5. Derivative of that is a 2. Nice and easy there. All right, now I want to take my f, x, y, and z, and I'm going to plug in x of t, y of t, and z of t. It just means put it in terms of t. All right, so we have, I'm going to put, we'll put it, keep it in ijk for a moment. I got -1 plus 2t plus 2 times y, which was 3 minus 5t. That is I got to scoot this over. Plus, all right, the next one was 2z. So I got 2 times 2 plus 2t. That's j. And then plus, we have x minus y. So -1 plus 2t minus 3 minus 5t. right? I'm going to rewrite this f in bracket form, right? If I combine like terms, I got it right here. 5 minus 8t, comma, 4 plus 4t, comma, and then negative 4 plus 7t. I would work all that out, simplify, see if you can get to that. That's f. I'm going to go ahead and write r2, r prime, was 2, negative 5, 2. So I can find the work now. Now we created these, so these were from t equals 0 to t equals 1. Right, and then I just dot those two things. So 2 times 5 minus 8t plus or minus 5 times 4 plus 4t plus 2 times negative 4 plus 7t. All of that dt. All right, I have one more step here that I'll put down. This is from 0 to 1. We can drop it because we don't have it. We only have one variable now. Negative 18 minus 22t dt. And then if we work all that out, we get a negative 29. Work can be negative in any way that anything else can be negative. Just put it in context of a perspective. Meaning if I was working, if we're counting the work I was doing, walking up a set of stairs, and then there was a gust of wind, an updraft that, made it much easier to walk up these stairs. Or think about maybe a headwind and a tailwind, right? Tailwind would take away from the work that you were having to do. Think about perspective. It's the same reason that we can have negative area, negative volume, is it's all about perspective.